Hello everyone, and welcome to this next video in the Houdini Academy Foundation module. In this video, I want to take the basic building shell that we have here, and I want to turn this into instance points so we can get started on the fundamentals of the tile building system in our tool. Now we're going to do this by first taking the outer building shape, and we're going to turn this into a point grid. Then we're going to use this point grid to build the basic tiles down here, the fundamentals of this loop. Now we have other systems in between, and we'll deal with that in the upcoming videos because that's a bit more complexity than I want to go with in this one. But let's get started on the basics first, and then we'll tackle that one in the video to come. So let's open up our scene and let's get started. Okay, so next what I want to do is I want to create a group on the corners of my building, on all the tiles that are at a sharp corner, in order to later on filter out those tiles so they won't spawn windows. And to do this, we need to actually grab the angle of the edges of my building. Now, if you recall from the Houdini 101 series on groups, we can do this using the group node. So let's go ahead and create a group node. And I'm going to plug this in below. And I will call this one group corners, or corner in this case. And I'm going to call this the corner group. Now at this point, the group node is selecting all of my primitives. So let's change that around as well. I'm going to change this to edge groups because in the end I want to select the edge that's on a corner first. And let's turn off the base group so I don't select everything, and instead turn on include by edges. Now in here we have the minimum edge angle. If I go ahead and turn this on, now you can see that I'm able to select the edges depending on the angle. If the angle goes over a certain amount, it will start to unselect elements. So what I basically want to do is that if an element is under an angle of 45, or whatever angle we set, it's going to select it, and then the tiles next to this are going to be marked so that they won't spawn windows. So let's go ahead and plug up this to the interface. Let's open up the type properties on my tool, and then let's grab the minimum angle and drag it in here. Now this is going to give me a angle parameter. Let's change that to a float because I'm not 100% sure if Unreal can handle this one. So I'd rather be safe, and frankly the angle parameter, as far as I'm aware, is basically just a float value with some limitations on it. Now in this case I'm going to call this one the corner angle. Like so. And I'm going to lock it between 0 and 180. Now we're probably not going to have 180 degree walls, but just in case, let's do this. Then under channels, I'm going to make sure that the default value is set to 45. Now to keep it organized and don't have all my parameters clutter up together, let's also add in a separator in between. So we split it up a bit, and let's click accept. So now, and let me hide these attributes for a moment. Now I have the ability to use my parameter menu to select or unselect parts of the walls of my building. So if I go too low, it will select everything. Probably not what we want. So we could actually remove the lower limit. Let's go ahead and change this to say 1 degree. So at the very least there needs to be a 1 degree corner before it will try to select it. So now we are at the very least sure we won't select every single flat wall at the same time. Then next what I want to do is grab my edge group and promote it over to the primitives next to it. And for that we can use a group promote node. So let's grab a group promote node. Let's go ahead and plug that in behind. And I will call this one promote corner as well. Let's grab the corner group from the group name. Now it's going to try to convert whatever group it thinks it has to convert. I want to make sure it selects the edge groups. And I want to convert this to primitives. Now that should already work. As you can see, it's now promoted it outwards to its connected elements and converted it from an edge group into a primitive group. That's exactly what I wanted it to do. And last, what I wanted to do is to turn this group into an attribute. So let's create an attribute create node here. Plug that in as well. And I'm going to filter out my primitive group, corner. Make sure it's at the primitives if you want to be sure. Okay. And then next, I'm going to call this one the corner attribute. Now, as you recall from the previous video, we could also do this through the output as integer attribute. But this is just to show you, once again, there are two different ways to do this. Either we can create an attribute create node, or we can do it straight through the promote node right here. Right now, I'm just going to do it through an attribute create node. So we go ahead and set it to primitive, set our type to integer, and I want to set the value to 1. So now under the spreadsheet, we should be able to see our attributes. Now we can't because before I locked my selection here. Let me unlock this. And now we should be able to see the groups right there. So here we go. We have our corner attribute available for the corners of our building. Again, if I go ahead and make a visualizer out of that, I should be able to see it right there. Okay. All this will do fine. I don't exactly need to see the number. In this case, it's actually easier to see it as a color. But for later, I might want to change it to a number anyway. So let's leave that for now. With this, I have a setup that works with groups. So I'm going to color these nodes green. And let's wrap these into a little netbox as well. So that's another section done. And I'm going to call this one the group corner edges section. And let's just make sure that everything has a proper name as well. Okay, so now what I have is the entire wall of the building set up. And now we are basically ready to start turning these into spawn points for our walls. At this point, we have our walls. We have all these attributes available on them. We have the width. We have the segments. We have the floor numbers, and we have the corner attribute as well. So that's cool, right? We have all this information. What happens if we try to turn this into spawn points? Well, we need to go through a little process to make that work. And for this, I need to run it over every single primitive of this building. So I can, for every single primitive, have it extract the attributes and then create a spawn point for that particular piece of the building, that particular tile. We can do this using a for each loop that runs over primitives. If I drop this one in, then you'll notice that this particular one doesn't come with the count block. And that's because this one automatically runs over whatever primitives you give it. It's been pre-configured to run by piece or point, and then it runs over the elements, in this case the primitives. So to go ahead and plug that in, and I'm going to call this one for each primitive, like so. So now, if I set my for each loop to single pass, and I switch my wireframe on here, then you can see that it only creates one primitive, because it runs over every single one. Inside of this loop, for every single iteration, there's only one primitive available. So we only have one primitive number as well. And it will slowly pickwalk its way up the primitive numbers. It starts at primitive number 0 and then moves its way up until it's reached every single primitive, right? If I go ahead and limit the amount of iterations on this building, you can see that I can also just make it assemble the building like this. This is interesting if you want to create some kind of animation maybe, but in our case, all I want to do is run over every single one of these tiles. Alright, so at this point we have our for each loop ready, and now what I want to do is create a spawn point at the very bottom of each of these tiles. Now let me go over to my example project and I'll show you what I want to do. Over here we can see we have our points and we have a wireframe representing the original tiles, right? Now each of these points still has attributes on them because I have promoted the attributes for the width and the segments as well as the corners and the floors to these points. So all of that is still working. Now they also have normals that came from the original primitives. So if I grab the original primitive and look at their normals, and this is a bit hard to see, so I'm going to press the D key, then go to guides, and I'm going to boost the normal strength up to 1. So I'll make it a little easier to see our normals here. Okay, that's better. So now, if I go and show down here the result, you see that every single one of these points has an outward facing normal. And we need this for our tiles later on, so our tiles will spawn in the right orientation, facing the outside of the building, right? Now next, what I want to do is make sure that all these points originate from the original primitive. And we're going to do that using a couple of different nodes in this order here. If we take the for each loop and we grab a fuse node, we can first snap all of our points to the center. And then we can fuse them together. Now I'm doing this because the fuse node by default doesn't have proper behavior when you just try to fuse. If you want to snap them to the center of the tile, I noticed snapping is the best way, and then you can fuse them after. So anyway, let's go ahead and do this in our own scene, and I'll build it there. So the first thing that I would like to do is take my loop and switch it over into single pass. And if I do this, I isolate out just one iteration, so I can work with just that one. Okay, it just makes it a bit easier. Then let's make sure that we are watching our points and our point numbers as well. And now we are ready to start working on this. Now the first node that I want to place in order to collapse our points down to one another is the fuse node. And the fuse node, if you might recall from the Houdini 101 lecture on common attributes, has the ability to take all of our points and snap them to one another. Now by default, the fuse node, if we were to increase the snap distance, is simply going to make our geometry disappear. And that's because our geometry is way too simple, so the moment it snaps the points together, our geometry no longer exists because it's basically 0 size, and it will be destroyed. In order to fix that, we can actually turn on keep fused points, and then it doesn't care about the geometry. So that's one way how we could do this. However, by default, it's simply going to snap the points to one another, and that's not the behavior I'm looking for. So let's go back to set this to a low value and turn this back off. And instead, I'm going to make this node snap points instead of fuse them. If I turn the fuse node into snap mode by turning the fuse snap points option off, and then I increase this value, it will start to collapse the points down towards one another. And eventually, they will collapse down towards the very center of our primitive. So there we are. We now have 4 points sitting all right on top of one another. Okay, so we have our points, and technically we still have our primitive because they were not fused, right? There's just 0 space in this primitive at the moment. Okay, so now all the points are snapping to their center. I just want to make sure that before we continue, we also turn off snap distance altogether. And when we do this, then the points will always snap to their shared center. So we don't have to worry about this anymore. So now that the points are snapped, we still have 4 points. Let's go ahead and fuse them. So let's create another fuse node. And this fuse node, we're going to keep on fuse mode. But as you see, it's going to destroy our primitive. So to fix this, I'm going to turn off the remove repeated vertices and degenerate primitives toggle. And in this case, it's going to basically remove our primitive, remove all the other vertices, and only keep one in place. If we were to use keep fused points instead, it would still keep 3 points around in order to maintain that primitive that was already there. So by turning off keep fused points and turning off remove repeated vertices, we're going to keep 1 point, and that's what we want. And since this is actually a fuse node, well, I'm going to keep it with the name fuse. That's fine. Now we do have one problem though. At the very start, we had a primitive, and that primitive had a series of attributes, right? We had the corner, the floor, segments, width, and even a couple of groups. I still want to maintain those attributes. Now I don't care too much about the groups because we can recreate them from the attributes, but I do want to keep the attributes. So let's create an attribute promote and promote these attributes from the surface to the points. Over here, let's call this one promote attributes. And then on the settings, I want to change this to promote the primitive attributes. And I want to make sure I grab all of these. So corner, floor, segment, and width, actually. So in this case, what's going to happen is that the primitive attributes are going to be spread out to their points. And because there's no other primitive attributes next to this, we don't have to worry about the type of promotion. It's just going to send it over to these points. That's pretty straightforward. So now, on our points, we now have these attributes. If I go ahead and display them, we now have all of them present. Now in this case, the corner attribute is viewed as a color. Let me change this over to a marker. So here we can see we now have markers specifically for the corners, and everything else is also working. So I'm just going to give these unique colors so we can at least identify them. Okay, cool. So with our attributes intact, the last thing I want is the normal, right? So we need to know the normal of this primitive. And if I go ahead and collapse the primitive, then its normal is also going to disappear. So let's grab a normal node, plug this in, and let's compute out the point normal. So now we can see the forward-facing direction of this surface reflected on our points as well. And if we fuse it all together, then, well, we are maintaining our attributes down here, but not our normal. And that's because the fuse node, by default, recomputes normals. And because there's no primitive, there's no normal to recompute. So let's also turn this off. And we need to do the same thing for the fuse node as well, because both of them are computing the normals. Okay, so now we actually have the normal, and we have the attributes. Again, let me just pull them up. There we go. So we have all of them available. If I now go ahead and plug this into the end of our loop, and I run the end of the loop, turn off single pass basically, then now you can see that we have attributes for the entire building, and it's quite a lot of information. Let me go ahead and make this a little bit bigger and maybe only show a few of them at a time. So we have the width value right here. We have the segments. We have the floors and the corners. So we know where everything is. All right, so at this point, we are almost ready. the last thing I want to do is make sure that these points are snapped towards the bottom of my tile. And we can do this really easily by creating a transform node. Let's go ahead and create one. And I want to plug it in below my fuse node here. Now let's call this one the floor bottom. And what I want to do with this, and let me quickly make a bit of space here, is to take the points as they are inside my tiles, and instead of having them at the center of our tiles, I want to move them to the bottom of each of these tiles. So if I take my height translation here, the Y channel, and I reduce it, then I can set the points on the bottom of each of these tiles really easily. I just have to take half of the height of my tiles. So if I grab that value from my parameter panel here, I can copy that. And then in here, what I want to do is basically paste it in. But of course, the default value is going to offset all the points up by one tile. So let's change this equation. Let's say negative the floor height times 0.5. And this will of course lower all my points by half the floor height. So now my points are at the bottom of their tiles, and with that we have this ready. So let's go ahead and wrap this inside of a new netbox. And let's call this the spawn points. Alright, so let's move on to the next part. Okay, so to wrap up this video, what I would like to do is build the first part of our tile copying mechanic that will allow us to generate procedurally our tiles from these spawn points. Now, before we created our basic wall shell using a simple copying mechanic, but this is just the guide for the height and width of our tiles. And we've actually translated that, of course, into our attributes down here. Now we can use those attributes to regenerate our tiles procedurally. Now the way how we're going to do this is through a for each loop that runs over our spawn points right here. And in this particular lecture, in the foundation course, I'm going to use a mechanic that isn't the most optimized, but is still very simple. Now later on in the masterclass, I'm going to optimize this mechanic much more, and we will definitely use very powerful and optimized tile instancing. But for now, I want to show you the basics, and the basics are a bit less efficient. Regardless, it's still going to work. So let's go ahead and start building this. What I would like to do is create a for each loop for points. So let's call up a for each loop and bring up the points version. And just like before of our primitives, if we connect this up, we can use the iteration or single pass here to see that the points are basically walking up the building following their point numbers. So every iteration runs over every point number. And of course we can still grab a single pass as well. So that's what we'll be working with, right? Every single point. Now let's grab this loop and let's call this one the tile begin and tile end. Now I'm going to create a little bit of space here. Let's pull this down. And next, what I want to do is copy a very basic square or grid onto this point. And we can do this using a copy to points SOP. So the copy to points SOP will allow us to take a shape going into input 1, the geometry to copy, and then copy it to the points in input 2. So if I grab a grid, And I plug that into the first input. And then plug the current point here into the second input. And I look at that. You can see how right now it is basically copying my grid onto that point, and it will copy it based on the original world space coordinates of this grid. So if I look at that grid and I hide everything else, you can see how it's currently located at the world center, and its pivot point is basically what's being copied onto my current spawn point. So if I grab my spawn point and then I wireframe my grid, you can see that it sits perfectly in the middle. So that's how the copy to points works. It copies whatever you have with its pivot point onto the current spawn point, onto the current point that it's running over. Now it can actually run on multiple points at the same time. I could plug it in directly to this node over here and it would work. You can see I'm basically inundating my building with grids, and this isn't really what I want. Now I could of course grab my grids and reorient them. So let's say I change this to the YZ plane. Okay, and then let's reduce the rows and columns. So we have a slightly less dense grid here. And let's reduce the sizes of these down as well. So let's make them 1 by 1 for starters. Now we can see right now, if we wireframe the original building, like let's say grab it from here, that they're being copied in the wrong orientation. So let's change the grid to the XY plane instead. And now they are actually aligning to my original building shape. Now the reason that all these grids are pointing towards the inside of my building right now is not just because of the original orientation of the grid. It's actually mainly because of the spawn points that are located on our building and their normals. So as you might remember, we made sure that we actually copied the normal from our original tile, which is pointing outwards, onto our spawn points. So our spawn point has an outward facing normal. And the copy to points node uses this to then orient whatever you're trying to copy. Now in this case we are only using the normal attribute, but we could also use the up vector to change the roll position of these particular elements. And let me quickly show you how that works. So let's create an attribute create node. And let me quickly plug this in. So these are going to be my temporary attributes because I'm going to remove this later. We don't need them right now. But if I create a up vector, which is going to be a point attribute, vector type, and then I change one of these values here. Let's say I first set the up vector to be straight up. So X, Y, Z, this value is going to be up towards 1. Now in here, in my point attributes, you will find the up vector exists. Now if I go ahead and change one of the X or Z values, you will notice that my grids here start to rotate. And that's basically because I'm changing the orientation that the up direction of this grid is supposed to point in. Now I'm going to turn this back to 0. And next to this there's another attribute that controls the basic copying behavior of the copy to points node, and that is the p scale. So let's add another attribute here. And I'm going to call this one p scale or point scale. Now the moment I do that and it's set to 0, all my grids are basically reduced to a size of, well, nothing. They're still there, they're just really tiny. So if I increase this, you can see how I can basically scale my grids. So this is one way how we could actually size up our grids to be the correct size, right? But this is a uniform scale, and that won't work for us. Then next we also have the scale vector tree attribute, or rather a size tree attribute. So let's go ahead and add that one too. And this one, if we look at scale, not p scale but scale, is a float size tree attribute. And if I set this one to 1, 1, and 1, then we can effectively control our grids in independent directions. So we can either scale them up or down, or we can scale them sideways. And this will affect the entire mesh, right? So whatever we feed in here is going to scale based on these values. Now, I'm not going to work this way, and I'm going to do that intentionally. Now, I'll talk about it more in a minute. But this is basically how you would set it up if you're trying to load pure instances, like actual meshes or something, and you want to scale those, or you want to orient them or position them. So let's get rid of this. And yeah, let's have a closer look at our grid itself. So right now, these grids are basically orienting towards the positive Z direction in the world. So if I look up close to my grid here, where it is located, I can of course use the grid itself, but this won't tell me the direction that I'm looking in. And here in the corner, you can see this little gnomon in the corner for the directions, but it's overlapping. So you can also pull up another one that's native to the world center. We can do that with the D button. Then we go to guides, and in here we can find the origin gnomon as well. So if we enable this one, then now in the center of our world, we are going to get this directional marker. I don't always have it turned on because it can get in my way, but it can also be useful. So now right now this plane is in the negative Z direction. Its forward facing side is facing away from positive Z. I don't mind this because we're later going to extrude this one. And then the shape itself is going to be pushed inwards into the building. Because right now when I copy it onto my building, you can see how all the planes are facing inward. This is actually a good thing for us right now, so let's keep it that way. Now, if I were to take my grids, what I could do is first raise them up on top of their original spawn points. If we look at these spawn points, they're located here, and I want to move my grids on top of them. So just like before, when we used the floor height, we can now use the floor height again to raise these grids up. So let's set up these grids here so they will actually work. And to do that, let's grab the parameter from the interface for the floor height and copy that again. And then I'm going to set it onto my grid right here. So in its size 2 or size Y value, let's paste this in. And then what I need to do, of course, is to raise them up so they're sitting on top of their own individual grids. I'm going to grab the center value, plug in my height as well, and then let's multiply this by 0.5. So we're raising them up by half. So basically what we've just done is we've taken this grid and we made it sit on top of the world center, like so. Now this will deal with the height of our tiles, but it won't deal with the width. And the reason I want to wrap it inside of this loop to begin with, and not just keep it outside of the loop like we have right now, is because I cannot control directly the width value. There is something we can do with the point scale, but this would scale both in X and Y. In other words, in the width and the height value, and I don't want that. Plus, I also want to control other aspects of my tiles, not just the copying behavior here. So I'm going to put this copy node inside of the loop and then process everything in there. So let's go ahead and hook it back up. So now, since we're working inside of the loop, we're only going to see one iteration unless we are rendering out everything at the end. If we were to plug it in like so, and then turn off single pass, we could still see our result. But what I want to do in this case is I want to take the width value right there, and I want to link it up to the width value that's currently present on my points. So let's visualize that one again. Under visuals, let's bring up the width value. Okay, so let's have a look at one point instead of every one of them by clicking on the actual loop itself. And right now we are running over this tile up here. In order to reference the width attribute that's currently on this point and send it over to our grid, we need to do another spare input connection like we did in the last lecture over here between the detail attribute and these transform and attribute create nodes. Now in this case we aren't dealing with a detail attribute, we are dealing with a point attribute. So that's this one here, the width attribute. And to sample that, of course, we need to use a point expression, not a detail expression. Alright, so let me call up Notepad again. And just like before, in the previous lecture when we were using the detail expression, up here we have the other expressions for the point, primitive, and vertex elements, respectively. So the top one is for the points, and that's the one we're going to use right now. So over here we have, of course, the node that we need to reference the attribute from, which is going to be from here. So that's going to be, again, another spare input. So I'm going to set this to -1. Then it wants to request the point number to sample from, because of course, if we have multiple point numbers, we need to know which one we actually want to grab the attribute from. In this case, we only have one point because we are running a for each loop. So I'm going to set this to 0, 0.0 basically. Then we need the attribute name. Now we know that the attribute name in this case is width, and because it's a string, it's inside quotation marks. So we just put it inside quotation marks like this, and it'll work. And then finally, of course, we have the index, just like before with the detail attribute. Since our width attribute is just a single-sized float value, we just give this a value of 0 as well. So this is the little expression that we are going to use, and I'm going to copy this. So over here on our grid, let's go ahead and set this up. So here on the right, we have the size, so we can paste our point expression in there. Now right now, of course, it's looking for the node it wants to reference, so we're going to add a spare input. And as for the node that I want to reference here, I could hook it up directly to the for each tile begin node. But because I have other nodes inside this loop later that are also going to need to get attributes from here, I'd rather set up a dedicated null node as a data carrier. And I like to do this to keep my networks organized because I know where I'm grabbing all my data from. So inside of this loop, let's create a null node. And I'm going to call this node the tile data node. Let's plug that into the beginning. And because it's going to be a data carrier, I am going to color it blue. Now, as for this grid, this is actually going to be my tile frame. So the main frame for my tiles. Let's call it tile frame. So that matches. And now I need to set up this grid here to reference my tile data so it can grab the width attribute that we can find, of course, on here. So let's just say / tile data 1. Oh, 2 dots, not 3. Okay, there we go. So now if we look at the copy to points node, it should be getting its correct width. And if we look at the end of the loop, now it's covering the entire building. Now these numbers are getting a bit in my way, and now they're on all the points, they're everywhere. instead of just the primitive centers. So I'm going to hide them again. Now, like I mentioned, all my grids are currently pointing inwards. And normally you'd think that's wrong, right? Because they should be pointing outwards. It's the outside of the building after all. But our building is actually going to have some depth, and it's going to have an interior as well. So what I actually want to do is extrude these tiles inwards. And I can of course do that with a poly extrude in the most simple way. Okay? So let's create a poly extrude node. And let's plug that in. Now with this poly extrude, I can set the distance value. And if I increase this, you will see that I'm actually adding some depth to my tiles. Now, right now, we don't have the backside, so let's turn that on over here. And there we go. We now have a basic wall with a bit of depth in it. Now, I'm intentionally extruding these tiles inwards, and there is something to be said about extruding inwards or outwards, but we are going to get some of these gaps. In this project, I'm going to keep this particular component relatively simple, but by the end of the course you are free to make adjustments yourself, and in the final main masterclass we are going to revisit this entire system with actual instance tiles, but for now I want to keep it simple, so we're going to keep it like this. You are of course free to adjust the tool later when we've completed it, and I'd be happy to see what you come up with. Okay, but for now, what I have here is my poly extrude, and the second thing I want to do is make these into little windows. Okay, so I can grab my poly extrude and I want to add another one above it. Let's plug that in and let's look at the actual tile itself right now. So if I grab this node and I, instead of extruding outward, I extrude inward, like so, I can then remove the front side and only keep the sides, and this will create a little window frame. So now if I go ahead and look at the entire building, and I were to hook this up, then presto, we immediately have all of our windows, right? The basic model shape for our windows. Now I'm not going to go too far with this at this point. We will revise this in the next set of videos, because right now I simply don't have all the attributes that I need in order to properly configure this building. I'll quickly show you what I mean. So here's our main example project, right? And we have all these different types of elements. We have the doors down here, we have these windows, then on the upper floors we have other windows, we have the balconies, and each of these is actually a different kind of tile. In fact, the windows on the upper floors are a different set of windows than the ones on the bottom. So each of these is basically a different kind of tile that we need to define. And next to that, of course, we also have our windows missing on the corners on the upper floors of our building. So all this information we still actually need to create. So in the next lecture, what I want to do is set all of this up, because what we have right now as basic information is not enough. And then we'll take this and we'll revise it. So I'm going to grab this network and I'm going to drag it out of the way for now. I'm going to disconnect it, and then we'll look at it again after we've completed the next video. So thank you for watching this particular video, and I hope to see you in the next one. Thanks for watching and have a good one.